This presentation is not going to talk about any web-based things. This presentation contains only 2 lines of Python code, and this presentation also contains evolution theory. So if somebody is not comfortable with that, please leave. Okay, so the first thing first, this man is the man behind ZeroMQ library product. That's his Twitter, and he's not between us anymore. And basically, when I was creating this presentation, I was kind of thinking that it's a great deal that we are here just once, and our time here is limited, yet. So, what's the most dangerous thing everybody does? Anybody have an idea? Driving. No, but more generally. It's living, exactly. And another one is basically saying, yeah, sorry, there's a mistake. So there's a possibility, that there might be a possibility that there will be artificial light quite soon. What do you do for a living? I earn money to support my wife and offspring. Everybody else is doing their own stuff. Is it planned? Is it something you just live, or what? How you get, for example, into this conference? Why you are here? Why you are spending time here? There's a man called Ray Kurzweil. He's American. He's came up with such a chart saying that, okay, well, we found life. There was some kind of a progress, and he's just saying that the progress is getting exponential. That's one of the charts I've got. Moore's law, I guess everybody in this room should be aware of. Basically, it says that every, I think, 1.5, maybe 2 years, the density of computation for the same amount of money is doubling. So that's why they claim it's exponential. Just when you see the chart, I don't know if everybody can see it, on the y-axis there's a logarithmic scale. So it's not linear, it's exponential. This is my update from some internet resources, because recently people were claiming that speed up of general processors is not big enough to be in Moore's law. I made some calculations, gathered some resources in floating point operations per second. It's how many calculations you are able to do for, one floating point operations per second and price for that. So in 61 it was $8 tera. I invented that. Then 83 was 43 million, then 42,000 in 97. 2007, 52, and 2015, it was some Celeron something, not a big deal computer with, I think, Radeon GPU graphics, and they calculated that it's just 6 cents for a gigaflop. So it seems like that Moore's law is still in work. This is what I've got from Nvidia marketing just yesterday. That's the speed up they claim they've got in their latest Pascal-based graphic card. I think it's 1080, something like that. So it's getting up as good. This is a chart from Ray Kurzweil work as well, and he's claiming that somewhere around, try this, somewhere around 2020, we should be able, by hardware which costs $1,000, to be able to do as many calculations as a human brain is able to do. Is it achievable? I don't know. I would guess so, because we are somewhere here. I would guess we are kind of able to generate as many calculations as they are needed for a mouse brain. This is something completely different, but connected. When you do program something, you probably put some effort and time to create that program, get bugs done, basically finish your work. There was a study, we've got source down there, which says that generally every circle here, this one means an individual who was working on that particular problem. So for C and C++, it was somewhere, 256 to 5 something lines of code, and work time was around 8 to 16 hours. For Java, it was more or less the same, I would say. And for script languages, and by script languages, they had Python, they had TCL, and others. I don't recall. So generally speaking, with Python, we are fine. And we can do things quickly. That's another interesting chart. It's again about time. Basically, you can, according to this chart, you should be optimizing your time you spent on automating things. So I just took one example. If you do for 5 years weekly something for 1 minute, you save 4 hours if you automate that particular thing. If you, and in my words, I would say, if you automate a thing which takes 1 minute and you run it weekly, it doesn't make any sense to work on that particular automation for more than 4 hours. That's my take from this chart. It's a great chart to show your bosses in case they require you to work on something which doesn't make sense at all, because you basically spending time for nothing. That's another thing about time. Whoever waited for the computer to finish something. Calculations, copying. I know internet is quick these days, but not quick enough. But it's not the full story, because there's a network disk, then there is a L3 cache, L2 cache, L1 cache, and then there's a CPU. And it gets worse. When you do program, or you're creating something, bear in mind these scales. So basically, if something is in the processor and you calculate 1 + 1 or 1 + 2, whatever, it's very quick. But for example, if you need to load something from the memory, it's already 100 nanoseconds, sorry. There's also interesting stuff about L2, L1 cache. There is no mentioning about L3 cache. Just one interesting example. I was interviewed once about these things, and basically the question was, what is quicker? If you got a matrix in the memory, and you are trying to do like a full scan of the memory, what's quicker? Do like rows, and then columns, or columns and then rows? And my answer was that rows then columns. I was kind of expecting that memory is sequential, But my answer was correct, but on wrong premises, because the correct premises is that the more data you keep in your L1, L2, L3 cache, the better. And because L1, L2, and 3 are being loaded from the memory like in chunks, it's always quicker to use rows instead of columns first. Keep your program as close to the CPU core as possible. That's an idea about this one. Also, there is another thing. A lot of programmers keep their data in the databases. Just keep in mind that round trip within the same data center takes 500 microseconds. If you have these round trips all the time and you add things like getting the data from the database, because it takes some time database to process your data. It also takes some time in Python case to change the data from the wire format to Python objects format, be it string or be it float or whatever. And just all this add up. So if you are able within your program to keep stuff in the memory, then you will be much quicker. Even with Python, I would say if you've got a C program requesting something from the database, and if you've got Python program doing exactly the same, keeping the data in the memory, it's much quicker. And you will beat those C guys. This is the example how one of my projects was solved by interconnecting or bridging components just to reuse already done things. There was a proprietary Java-Lib component, and I was able to wrap it up with Cython or Cython, or I don't know how it's spelled, and using this RPIT's remote procedure call library, I was able to speak directly with another instance of Python 2, where I've got, oh sorry, there is another mistake. This should be Numpy, with standard libraries which are available in Python, and you can do really quickly things which you wouldn't be able to do directly with Python. So that's one example how do things easily without too much hassle. In my case, saving time. This is another example. There was this project is work in progress. There is a multi-threaded C server with customized C plugin to intercept basically the data which are getting in and out. It's just getting this session ID from each packet and channels it through 0MQ to many channels, and they are just Python clients. I can instantiate how many clients I want, and all these clients will be getting very quickly updates. There's no problem with if you got a server with many cores, you have no problem with GIL, you have no problem with all that things which you've got problem with when you've got big code and you are not able to get your data straight and stuff like that. All these Python free clients, they are very, very simple. They are just getting messages from 0MQ, sending their responses, and they are done. At the same time, these clients keeps all their stuff in the memory, so it's everything all the time is Python. There's no requests to database which will keep your sessions or share the data between sessions. Database is just for failover or restart. So in case something goes wrong, for example, all these clients, they are running in virtual environment, and it can happen that the virtual environment goes down, then the second image will be instantiated. You will get your Python client started. They will just get their session data from the database, and since that they can run and run and run. So I'm just saying, make bridges. Don't reinvent the wheel. Premature optimization is the root of all evil. There are a lot of projects done in C, Java, whatever. You just need pieces from those projects. You just need information and data, and it's just easier not to reinvent another library done directly in Python. It's just easier to just bridge them somehow and reuse existing work. Generalized idea, and it's also for the life, I believe. Be the master of puppets. Just use what is already done, what is existing. Organize it intelligently, and it will do you good. If it doesn't do any good, you will at least learn something. Now, something completely different. There are financial markets in the world. Simply, they trade stocks, futures, options. There are many of them. You can do analysis on top of those instruments. It can be fundamental analysis, which is more or less seeing the company, saying, okay, this company earns this much, and their profit is this much and that much, whatever. It's very complicated. Usually you should have MBA to understand their order analysis. Then there are also people who believe that the price moves, this is the example how price move can look like, is behaving somehow, because in the end of the day, on the markets, there are traders who, or I should rather say, not just traders, there are algorithms which were done on behalf of traders. So that's what technical people believe, is that they see something like, I don't know, there is a pattern like this, and if I see this pattern like this in 1 or 2 days, I should see that the price will go down. And the whole business behind that is that you should buy low, sell high, or sell high and buy low. And of course, learn money. Technical analysis, in my work, I was using Ta-Lib, which is C optimized library for calculating the data. There is also a Python component which allows you to use this Ta-Lib. You can have different indicators. They are called trend, momentum, volume, volatility, patterns, signal processing. If you ever come across this term, simply it's you've got a time series. You've got time here on X. You've got some price on Y, and this example is a moving average. Basically, I don't know what's the parameter of this moving average, but for example, if I take this part, I would say that from here to here, it's just making the average value, and the average value is this one. So it's like you've got a window, and it's moved on top of the time series, and you are calculating averages. Same is for, that's the example of volatility. You can have small volatility in a way that volatility means that you are considering how much stock or whatever moved up or down. You don't care if it's moving up, but you care how much. So as a result, you get some charts like this. Now something completely different. Evolution-inspired algorithms. Basically, these algorithms are trying to mitigate what the nature done to us. So it has got some kind of a generation, or you've got the number of your individuals. You will get into, you will simply measure every individual, saying how fit he is in the generation. Like, you can have different fitnesses. They call it replacement, meaning that you are simply like simulating what is the word? Matches between two individuals. Like, you randomly select two individuals, match them together, or do some stuff to them, and the result you evaluate again. And of course, that miss and match in the replacement is then goes to stop criteria. It's not important, but it goes to selection, and again you evaluate your individuals, and individuals which you consider the best will kind of survive into the next generation, and the rest will kind of die. So that's how evolution-inspired algorithms are working. This is genetic programming. It's more or less the same. I'm sorry about quality of this picture. I couldn't find better one. It's more or less the same. You've got some individuals here. These trees are representing programs, and those programs are mixed together. You measure their fitness, and again you will choose if you go ahead with them or not, or what you're gonna do with them. There are basically two operations when you are matching two parents or the single individual together. It's basically you've got your individual 1, you've got individual 2, and I don't know if you can see how this particular function, or I should rather say a program, is working. It's basically SQRT on B multiplied by B plus A and divided by SQRT B plus B. So that's example of genetic algorithm, genetic programming individual, and simply in crossover, these parts are being split. So this part will be here in this individual, and this part will be here. So it's like you've got those two parents and you've got two children in the next generation. There is also a mutation. That's another one. You've got again just one individual, and you will cut, or I should rather say select something somewhere in the whole tree, and you will mutate it into something different. Still keeping some of the old stuff in place. So in my case, I'm usually running 100 generations. Part of those 100 generations, there are around 3,000 individuals. That's about 400,000 fitness evaluation, meaning that in my evolution-based algorithm, I'm producing 400 100,000 individuals, and that's what I found. What works. Each individual, like these trees in my implementation, I've got 3 to 5 trees like this in each individual. It's for entry price, like a filter, stop loss, exit price, exit filter. It's running on high, low, close daily data. It's when I showed you how the financial market is moving, then this high, low, close is based on daily time frame. Then there's data which comes from 30 or 15 minutes time frame. These are primitives. Primitives means these blocks. Like we've got plus, minus, divided, multiply here. So I've got plus, minus, multiply, divided, less than, bigger than, equals, and all Ta-Lib. That's that library from the start. Also, I'm using deap library, it's called, and I'm using just this algorithm. It's really, if you get deep into it, you will know what this means. But honestly saying, I don't care much. I'm just using this one because it's producing the best results. There's another term called Sharpe ratio. It's being invented to so you'll be able, if you calculate Sharpe ratio, you will be able to compare two strategies, for example, of two funds. So I mean, even in your normal life, if you are not interested in genetic programming and you've got some money and you invest into funds, and you've got two funds, they usually provide you a return like, I don't know, 5, 6, 10%, and you want to be able to compare them. Sharpe ratio is the thing which will allow you to compare them properly, because it's not just comparing how much percent you've got in a month or year or 5 years. It's also comparing what was the progress, how you get into those 5%. So Sharpe ratio is bigger in case you've got more stable results. In a way that if you get a fund which goes like +1, +1, +1 every month, this one is going to have a better Sharpe ratio than the fund which has got +2, -1, -1, +3, and so on. And this one is Sharpe ratio rolling one, so over the years how it looked like. In my programs, I'm using modified Sharpe ratio to prefer individuals with more traits. That's the first Python line in my presentation. Simply, Sharpe ratio is just trait size divided by standard deviation of traits. I mean, what was the percentage of trade, how big profit you've got, and because all this is running on multi-markets, I mean, I'm not just using one market for the input data, I'm using many markets. Also, there are other possibilities what to do, how to test it, which I found are not that good. These are results. This is the example of one individual. So this is the text representation of a tree we saw before. So this one, for example, is the entry price for this particular product, and it's working with low price of previous day. On top of that, it's applying moving average with period 144, and on top of that, it's applying extended moving average or exponential moving average. I don't recall exactly on with this value. So that's one of the individuals. Important thing, it's working on these futures. So it's like oil, Japanese yen, and stuff like that. And for example, this strategy was generating profits between 2006 and 2014, except in 2008. I don't know how much. I was not able to calculate it, and I didn't have enough time. So future, I would say diversification, more markets, more strategies, going up in daily time frame, not to be stuck in 15, 30 minutes time frame, and deep learning possibly. That's the end.
Thank you very much. We have maybe like 4 minutes for questions. So what's the largest amount of money you lost?
That's no comment. But it was in dollars, and it was less than 10,000. So.
How to identify a process that is the right candidate for automation? What are the features to look for?
You have to use your brain, I'm afraid. I don't know. Everybody has got their own things, how they run stuff, and I don't know. For example, when I do program in Python, and to do things and automate in Python it's quick. Usually, when I've got example, I don't know. A couple of years ago, I was forced to work on some Excel sheet, and starting with like 200 lines, it was easier to program it than to do it in Excel. So it's difficult to say. It really depends what are the deadlines, how much you can risk. I mean, risk your time, risk your boss is going to be angry. It really depends. If you do your own project at home, you don't care. It's difficult to answer this one.
Can you recommend some library for genetic programming?
I'm using deap, spelled D-E-A-P.
Isn't 100 generations too few? Why 100?
No, I would say 100 generations is okay. It's my actually when you see how the evolution is going, usually around, I would say 50, 60 generation, you've got already pretty good result. At the same time, because all depends on statistics and randomness, you run one type of generation many times. So it's like, okay, I'm running it here, there, blah blah blah, and when I run exactly the same algorithm with different random seed, which makes a different random number line, then I've got completely different results. So it's all is based on randomness, and more or less it's statistics. Unix strength. I don't know what you mean by Unix strength. Unix strength? That was typo. I'm definitely sure about that. No. Algorithm. Well, this is just a preparation for algorithmic trading. It's not like finished. You still would have to do because that formula you saw a couple of slides. This one is just a formula, and you would still have to get this individual and implement it in your trading algorithm. In a sense, not trading algorithm, but your trading library, your trading thing. Okay.
Okay, I would probably stop here. Yeah.
And that is also about this memory thing. Yes, well, algorithmic trading is about keeping stuff in memory. The best to keep stuff in L2 cache, as close to the processor as possible.
Thanks. Thank you very much.